So at the beginning of the day this morning, I talked again about Fountain and David. And now I want to talk really about how we can combine these two. So in the sort of overall arc of third era of survey research, we're now in this part of the arc. Will big data kill surveys? I hope I've convinced you that the answer is no. And in fact, I think a better metaphor than one thing killing another thing is peanut butter and jelly. So for all the Americans here, I hope you grew up eating peanut butter and jelly sandwiches because they're so delicious. So peanut butter and jelly are examples of things that are complements to each other. So the more peanut butter you have, the more jelly you want. And likewise, the more jelly you have, the more peanut butter you want. It's not that one will replace the other. It's that they're complementary. And so I think we can think of it also as digital exhaust and big data sources and surveys are like peanut butter and jelly. And so I want to talk more about how this different recipes for peanut butter and jelly sandwiches. I think there are really two main recipes. The first is what in the book I call enriched asking, where you have some big data source, you have some survey data, and you do a one-to-one record linkage between them. And so in this case, then you use the entire thing for research. So this is a very natural model. I think this can start sometimes with the big data source, or it can sometimes start with the survey. And this is a model where you have to do sort of record linkage. Here is amplified asking. And so this is more like the Blumenstock study that I talked about on the first day, where you have some big data source, you have a small amount of survey data, you use the survey data to build a model, and then you use that model to impute the survey data for everyone. So in this case, I want to highlight, though, what is the role of the big data source? So here, you directly care about the big data source. It has stuff that you will eventually use in your research. Here, you don't end up using the big data source at all. So once Blumenstock used the big data source to impute this survey data, that was it. No more phone records. Just focusing on the survey data and the imputed survey data. So this is, I think, one of the biggest differences in the way that you combine these things. And also, what that means is that this big data source can be anything, even something that you don't care about at all. So like, let's say he could have records of like people's browsing on the internet or something. You might not care about that at all. But if that can be used to predict a survey answer that you care about, then it can be useful to you if you're using this recipe. And so what I want to talk about now is I want to talk more about this design. This design, I think, is good, and I think this will be used a lot. But I think that you don't need to hear me talk about this very much. There's a lot of issues. I talk some about them in the book. But I want to talk a little bit more about this, because I think this is a bigger change in mindset. And so we'll spend our time on that. So now we're going to see the paper we saw before, but hopefully I will explain it to you in a different way and get you to think about it in a little bit different way now. So as I said last time, starts with the call records. 1.5 million customers of this mobile phone company. Getting access to this call records is potentially one of the hardest parts of this research. Call records don't have what you want. You're interested in poverty. So you do a survey of a randomly sampled set of people from these call records, and then you link them together. So I want to talk a little bit more about the feature engineering process. So here, one way you could do it is you, as a researcher, could try to think of what the right features are to predict this outcome. So if you're not used to machine learning, by the way, you can just think of this as a linear regression. So I want to build a linear regression that's going to predict some measure, a continuous measure of poverty. And I want to know what are things about people's call records that could go into that linear regression. So you might think number of international calls versus number of domestic calls, or something like that. He was worried that he might not create all the right features, and so they created like this vocabulary system for creating features. So they knew that days of the week might be important, but they didn't want to to specify that in advance. So they said, OK, we're going to take every possible day of the week. And then we're going to take, let's say reciprocity is a measure that you would be interested in potentially. So how many of the people that you call you back? Or how much are you just calling other people? Or how much are they calling you? So those are two different features, like day of the week or reciprocity. But then he combined them. So he had reciprocity for every single day of the week. And then you could imagine adding in more things into this sort of vocabulary of features, which you then sort of automatically generate a huge variety of features, some of which make sense to you as a researcher, some of which might not make sense to you. You could describe what they are, but it's not clear why they would necessarily be important. And the reason they did this process is they wanted to be open to new features that they hadn't thought of. Then you build a model. So now we have a problem that they have an enormous number of features. And so then you can run into issues of overfitting, which we'll learn much more about on Friday, when you will do this process of building a complicated machine learning model from a high-dimensional data set. And so they did a certain kind of thing to prevent overfitting called, they did elastic net, a kind of regularization. We'll talk more about it on Friday. But the point of this here is that if you're going to do this more open-ended feature creation process, then you need to account for that in how you do this modeling step. Okay? Then once they have the model, they impute everyone's answers. They then impute the residence location. And then then they do this. This is a cross-validation result that I showed you before. So how well, for the people in the sample, if you pretend you don't know some of their wealth, you train your model, and then you try to predict the wealth of the people who you pretend like you don't have. This is how well it does. Not perfect, but there is some signal. The predicted wealth is related to the actual wealth. But again, this is not the quantity of interest. This is like a sanity check, basically. In a lot of computer science, this is often the quantity of interest. Here, this is not. This is a step in that direction. So then they were able to produce high-resolution spatial estimates of poverty. So this is a map of Rwanda. This grid is a 1 kilometer by 1 kilometer grid. So these are incredibly small geographic areas. And how well does this work? This is impossible to validate. There is no one who has produced estimates with this high of a resolution. And so when they compared to the demographic and health survey, they had to aggregate to a much higher level, to the region. So this is, again, if you're doing a new kind of measurement, it can often be very difficult to validate that measurement because no one has ever done that measurement before. So in the Xbox survey thing, we talked about how you can have some baseline that you're comparing against. Here, there's not really a baseline because no one's ever done this. And these actually never got validated, right? The only thing that got validated was the regional level estimates. And so here are the regional level estimates from their approach and from the demographic and health survey. And again, we see reasonable, but certainly not perfect results. This also, as I said, was 10 times faster and 50 times cheaper. I want to be clear, though, about where those numbers come from now. This was 10 times faster and 50 times cheaper if you don't, it depends how you count the costs. So, right, so like, I don't think Josh was paid while he was doing this. Everyone who's working on the DHS is getting paid. So like, as you, that changes some of how you would calculate the cost. It's also the case, though, that this would get much cheaper and faster as it became routinized. The DHS is very routinized. They've done it a lot. And so that enables them to bring down costs. I think in this case, the particular cost that's not included in this is the amount of time it took to get the data, which was enormous for obvious reasons, and also treat that data safely. So this is, again, a great example of combining ready-mades and custom-mades. Just leave this for a second. This is, I think, the future. Now, I want to talk a little bit more, though, about the trajectory of this research project. Because I've showed you the end. I've shown you the paper that was in Science and like the one that I personally think is just great. That was not the first paper in this trajectory. So there was the first paper in this the trajectory was about modeling churn. So for those of you who don't know about churn, is a big problem that a lot of industrial data science is related to. So if you own a mobile phone company and you want to, one of the things you might want to know is who is going to leave my company, because that is something you want to avoid. So what you have in your data, you have a bunch of call behavior, and you have a bunch of records about who has left the company or not. And so one thing you might want to do is you might want to have someone create a model that predicts whether someone is going to churn, and then you could potentially intervene and give them coupons or something so that they won't churn. So that was one of the first. Now, that may sound like that has nothing to do with social science at all. But the techniques that were used are very similar to the techniques that were used to measure poverty. So basically, in these churn models, you have some outcome, you have some call records, you have to do feature engineering, and then you build a model to predict the outcome from the call records. The only thing that's different is the outcome, in this case, in the poverty case, was changed and collected with a survey. So I think sometimes people see like a bright line between some of the stuff that's done in industrial data science and the stuff that's done by social scientists. And I think that bright line is not really that bright. Like slightly different ways of asking the question can mean a lot of these things can be repurposed to do social science research, or social science research techniques can be repurposed to do industrial data science. Then he has a paper where he actually does a first version of this actually related to predicting poverty. This paper, the results are actually pretty disappointing. Then he realizes he does some different kinds of feature engineering, he does some different kinds of machine learning, and then that leads to the paper that you see in Science. So the point is, you shouldn't necessarily expect that the first thing that you ever do with a piece of data is going to end up like this, and that often these projects involve a sequence of things, and things can get better and better as you learn more and go. OK? Yeah?
Why was the second one a disappointment? Was it like inaccurate or something?
OK, so the question is, why was the second one a disappointment? I will let you all, you can read it, but I will say one thing is, two things. One is they were trying to predict individual survey questions. And in the later paper, they were trying to predict wealth, which was an aggregate of survey questions. And it turns out it's much easier to predict this aggregate of survey questions than an individual survey question. Also, the feature engineering was improved from this paper to this paper, and the machine learning was improved. I think this paper, in computer science, often there are these conferences, and so they have deadlines. And so I think this was like, this is where I am right now, and we'll see. So now I want to tell you about something that has come after this paper, a new thing, which I think illustrates the generality of this recipe. So this paper came out, I believe, a year later, combining satellite imagery and machine learning to predict poverty. So a different big data source. We often don't think of satellite imagery as a big data source, but it is in the sense that it's something that's not created for the purposes of research. Like, in other words, let me just emphasize this a different way. When people think of big data sources, they often think of online stuff, like Facebook or Twitter. Sometimes they think about mobile phones, but really we should think about big data sources as anything that's collected at kind of a bulk scale and that's digital. And so this paper uses satellite imagery, and it's a really surprising paper, at least to me. But I want to talk a little bit about how you can see. I'm going to show you how they did this paper, but I want to show you how this paper is related to the Blumenstock paper and how it's related to lots of other things that you will encounter. And it's this idea from machine learning that's called supervised learning. And it's one that I think social scientists are not used to seeing, but it's one that comes up over and over and over again in computational social science. So basically, you have lots of pairs where you have some inputs and some output. And what you want to do is to learn a function that will allow you to predict the output from the inputs. So you could think about spam, for example. You have a bunch of emails. You have labels about whether they're spam or not spam. And you want to be able to build a model that will predict the output. So supervised learning can be, this is an example of a supervised learning task here, where you have this trace data, the call records, and you're using it to predict the survey. In a different part of Bit by Bit, in chapter 2, we have an example where there are social media posts, and we want to know about their sentiment. And so we hand label that sentiment for a sample of them, and then build a model, and then estimate the sentiment for all of them. So that comes up when working with trace data, big data sources. Here's something from the human computation chapter, which you'll read for Friday. This is about galaxies, labeling galaxies. It seems like it has nothing to do with anything we're talking about. So they have a bunch of galaxies. There's a way of turning each of those pictures of a galaxy into a bunch of features, like how blue is the picture, how much variation is there in their brightness of the pixels, how much of the picture is non-white, and there's all these other properties you can imagine. They have some hand-labeled classifications about whether the galaxy is elliptical or not elliptical. And then you can, again, imagine training a model and then essentially labeling all these other galaxies. So all of these are really the same recipe. And you can use this recipe in many, many settings. And now I'm going to show you how they use this recipe with satellite images, because it's actually an even more subtle and complicated version. So that's supervised learning. We'll get some practice with doing supervised learning on Friday. But for the social scientists who haven't seen this before, it's basically, a lot of it is just a version of regression, right? You have some, regression is a thing where you have inputs, you have outputs, and you try to train a model to match the outputs. It's a very similar thing. OK. So the question, though, would be, what if rather than trying to engineer these features by ourselves where we think about what they should be, what if we could just learn them automatically from the data? And so this is a very popular idea now, sometimes called deep learning. This is a nice review paper. Came out in Nature maybe a year or two ago. So they use this idea. So to get the information out of these satellite images, rather than trying to have a human expert say, OK, this is what this image looks like, this is what that image looks like, they tried to use deep learning. Or, as this headline in Vice, artificial intelligence is predicting human poverty from space. So you talk about the hype cycle. I think this is a beautiful version of this headline. Just to show you, satellite data is totally available. So here's a picture of Kigali, which is somewhere I went to do a research project a few years ago. And you can see that we can get, not only does there exist very high resolution imagery, we can get it like just on Google. You don't need to be in the CIA to have access to this data. So now let's imagine that we had data like this from all over. How would we use this to try to measure poverty? So in the past, people had used data about how much light there is at night. So imagine if you see a place where this is Manhattan, there's a lot of light there. That's a sign that there's potentially a lot of wealth. And if you look at other areas, like, for example, North Korea, there's very little light at night, and this is a sign there's potentially a lot of poverty. So people had used this night lights before to make estimates, but they don't do a very good job of distinguishing among relatively poor places. Like, there's potentially a lot of variability in wealth at the bottom end that's not well captured by the amount of lights there are at night. And so this prior research has used these night lights. And so what they did in this picture is they used this research. They used day pictures and night lights and survey data. So the trick that they had was a way of getting information out of these pictures during the day that would allow them to be able to create a bunch of features, which they would then connect to the survey data to do a prediction. So I just saw the sign that we have 0 minutes left, and I am also not an expert in neural networks, so I will not attempt to explain this in detail, but let me try to give you the intuition, which is you have these daytime pictures. You try to learn the features from these daytime pictures that will predict how much light there is at night. Then you use those same features and you combine them with a bunch of survey data from the Demographic and Health Survey, and then you are able to see the relationship between the daytime features, like is there a paved road or a dirt road? Are there tin roof on the house or is there wood roof on the house, or things like that. The neural network learns to distinguish those things. It doesn't put those same labels on them, but it learns these things from the pictures. And then you can combine that with the survey data. So let me show you you could obviously read the paper. They explain it in more detail. Here are some results from multiple countries where, again, they're using the Demographic and Health Survey data. This is the observed consumption. This is from the Demographic and Health Survey. And this is the amount of predicted consumption per dollar per person per day. And so you can see one of the nice things about this paper is they use multiple countries. So one of the things you might think about what the Blumenstock paper as well, that worked in Rwanda, but maybe there's something specific about that phone provider or something specific about the patterns of phone ownership in Rwanda. So here we see similar-ish patterns across many countries, which is promising. Here we see an important result where you can see if you train the model, a lot of these techniques require you to have some high-quality survey-based measure which you're using to train your model. So in other words, you can only do this where you already know what the right answer is. So that's a big problem. And so in this paper, they also go beyond the Blumenstock paper by trying to train a model from one country and then use it on another country, which is a much more realistic setting. So you might, let's say, get training data from Nigeria and then use it to make estimates about Tanzania. So does that work well? That's a very, very important question. And this provides some evidence that that works reasonably well. In other words, the results that you learn from one country can potentially be generalized and work well in another country, subject to all the caveats in the paper. So why have the computer learn the features? Why not just have a graduate student actually look at those pictures and label whether the roads are dirt roads or asphalt roads? And the answer is because of the way they scale. And this is another picture. So one schematic we'll see a lot is that supervised learning schematic. Another schematic that we'll see a lot is this, thinking about fixed costs and variable costs. So as the number of images increases, let's think about the two costs of these relative approaches. So the graduate student labeling approach has low fixed costs. Like we could start pretty much right now starting to do these labels. But then if you want to increase the number of labels by a factor of 10, you have to increase your cost roughly by a factor of 10. So it's low fixed cost, high variable cost. The approach that uses neural nets has the opposite cost structure. It's very expensive to get started because you have to learn all this stuff and train all these models. That's complicated. But then once that model is working, you can potentially do as many images as you want. So this allows you to work in a very different data regime where you have way more data than you're ever used to seeing. And so I think an exciting thing as researchers, we can think about what is it that we could do over here if we had 10 times more data, 100 times more data, 1,000 times more data than people have had before. But the only way we're going to get that is if we use these low variable cost approaches. That's the only way to get enormous amounts. Generally, these low variable cost approaches have high fixed costs, startup costs. And so I think increasingly we'll have to see how we can bear those startup costs so that we can then have this good scaling in terms of the cost per unit of data. OK, so all the code for that paper is available. And to wrap up, surveys and big data are complements and not substitutes. Sometimes we do enriched asking where we just stick the two things together. Sometimes we do amplified asking where we use the big data source to help make guesses about other people, and then we use those guesses themselves, and we don't care about the big data source itself. And you can learn more about these approaches in the What Comes Next part of Chapter 3. And now we have time for some questions, maybe. Yeah, good. We have time for some questions.
So this came in from the live stream earlier this morning. So Maddie from Helsinki wants to know how much openness and transparency we can expect from organizations in terms of the methods they use. Both sampling was the question, but also other types of estimation maybe. And Hanling from Chicago wants to ask you what you think about how to consider the temporal factor in the type of methods used to collect data. So going back to sampling, for example, in polling, we might want to see real-time trends. So how might different survey approaches have advantages over each other to consider temporal factors?
Sure. So temporal, let's talk about that first. So there, I think having a low-cost technique is really good. Naturally, right? So if you want to do more estimates, if you get the cost down, that's possible. The other thing about some of these approaches that combine big data sources and surveys allow you to fill in this kind of temporal trend. So for example, let's imagine that, let's take the case of the Blumenstock et al., the cell phone data. So let's imagine you've trained a model where you have features of cell phone calling records predicting poverty. And then you want to you could set up a graph that shows you that graph that we saw predicting poverty to this like micro regions of like 100 meter by 100 meter regions. You could create that graph and update that graph every day as you get new call records. Right, so you can have estimates basically continuous. Now, are those estimates going to be good? That's the important question. And here I think a very important thing to keep in mind about trying to do this thing is keeping in mind that the big data source itself can change. So let's imagine the company creates a new policy where they say, oh, we're going to have a new marketing campaign. We're going to have free international calls on the weekends. And the company may do that. It's a great thing for the company. And all of a sudden, your estimates are going to get totally thrown off. So the way to handle that problem is to continually recalibrate what you're doing. So you should never think that you're going to train one of these models and then let it run for all time. That's just a bad idea. And you should think that you're going to continually have to do recalibration. And I think this is actually a great ad for one of David Lazar's papers. So the Google flu trends, part of the problem that they ran into was they weren't recalibrating enough, and that Google changed its policies, and the modeling didn't account for that. So if you want these estimates over time, you need to continually recalibrate, and you need to be aware of changes in the data generating process. The first question from Maddie was about transparency, and I think that's very important. And very hard. So often if you want to buy, so often researchers are in a position where they want to buy access to a sample from a provider. So like YouGov, for example, is a company. You can go to YouGov and say, I have a survey. I want you to give it to 1,000 people. It is very hard so I believe my sense of things, I've not worked with any of these companies. My sense of it is that YouGov is a high quality company. They want to be transparent, my sense is. I don't think there are certain things that they can say. And I also I think that what they're doing is so complicated, transparency becomes very even difficult to imagine. Like at what point, if a thing is so complicated, it's hard to even be transparent, even if you want to be transparent. So I think in some ways, there has to be some trust involved in sort of if you're working with someone else to have confidence that they're doing what they're doing appropriately. And then in terms of transparency from big data sources, if you're combining them with surveys, you would often want to know things like from the mobile phone company about maybe they had in the past, they had these sales on weekends versus weekdays. Ideally, you would know that so that as you were training your model, you could account for that. Often that information is no longer recorded because these are new foo, new boo. Like the mobile phone company does not think like, oh, I need to keep track of what sales I ran 2 years ago just in case someone wants to do a bunch of stuff with historical data. Okay.